Hello everyone watching this video. Today in this video we'll discuss the moment of inertia for a solid cylinder. So here first I draw the solid cylinder. So this is the cylinder and we consider the mass of cylinder is capital M, length of cylinder is capital L and radius of cylinder is capital R. So here this is our cylinder and assume that this is the solid cylinder. That means the mass capital M is distributed continuously in the entire volume of the cylinder. So to determine the moment of inertia, first we take the axis, and in first case we take the moment of inertia about the main axis. So here first I draw the axis. So this is the axis which is along its length or perpendicular to the cross section area and passing through its center, or we can directly say the main axis of the cylinder. About it we determine the moment of inertia. So here to determine the moment of inertia, we first take a small component, or in this cylinder whatever the component we take, that should be a symmetrical and that should have a symmetry. So here we take a small mass component as a disc, and so we can assume that this cylinder is made of many discs and which center are at this on this axis. So I take a small component as a disc, and this disc, assume that this disc has a small mass dm and which is distributed over this area. So the moment of inertia about this axis for this small disc, I can write it as di is 1 by 2 dm r square. So here the moment of inertia for a disc we have determined, and we know the formula, which is half mr square, but the mass of this small disc is dm. So the moment of inertia about this axis for this small disc is half dm r square. So this is the moment of inertia, and to determine the moment of inertia for complete cylinder, we need to integrate it. So moment of inertia for this cylinder along this axis is di, and I put the value of di, which is half dm r square. Half and r square is the constant, and dm is the small mass component of this cylinder. So when I integrate it, the dm, I will get the complete mass, which is capital M, and the moment of inertia about the main axis for a solid cylinder will be half m r square. So this is our first case, and the moment of inertia about an axis along the main axis, which is half mr square. Yeah, this looks similar as we determined the moment of inertia for a disc. So here you are correct. When you see this cylinder from this side, you can see a disc. You can see a disc. So the moment of in this cylinder from this direction, mass is distributed as the mass was distributed in the disc. So in both of the cases, mass is distributed in the same manner. So moment of inertia is also same. Here in first case, I can take one more case, the moment of inertia along or about this axis. So this is the axis perpendicular to the cross section area and along the tangent. So here I can derive moment of inertia here by using this axis. So these two are the parallel axis, and I can use the parallel axis theorem, and I can write I is I naught plus md square. I naught is the moment of inertia about main axis, which we have derived and we know about it, and we are going to find the moment of inertia about this axis, which is parallel to this axis, and distance between two parallel axes is capital R. So it is very simple. I is I naught half mr square plus capital M mass of the cylinder, and the distance between two parallel axes is R. So here R square, I solve it, this will be 3 by 2 mr square. So this is the moment of inertia about an axis perpendicular to the cross section and along the tangent. So here in first case I took two cases, and in second case we will determine the moment of inertia along an axis perpendicular to the length and passing through its center. So before that I need to clean it up, and I clean it and I draw the circle again in this horizontal manner. So this is the our same cylinder of mass capital M, length capital L, and radius capital R. And here the axis about it we have determined the moment of inertia. But in the second case we take the axis, this axis about it we determine the moment of inertia. This axis is perpendicular to the length and passing through its center. So I write it about an axis perpendicular to the length and passing through center. So here it is our second case in which determine the moment of inertia about an axis perpendicular to the length and passing through its center, which is here. So before deriving any formula, we know that this is a rigid body, and for a rigid body we take a small mass component, and that mass component should be has a symmetry, and we can take that mass component anywhere in that rigid body. So here I take a small disk component. Here I take a small disk component of thickness dx. I take a small disk component of thickness dx here. So this is the disk component, and I can assume that this complete cylinder is made of different disks or many disks which is parallel to each other. So I take a single disk. So this is the mass component which I can take anywhere in this rigid body. So I am taking this, and which thickness is dx, and this is x distance away from this axis, and here I can write the radius r. So the radius of this disk is also capital R. So here first I write the moment of inertia about this axis for this small disk, which is 1 by 4 dm r square. R is the radius of this disk, dm the small mass or mass of this disk, and 1 by 4 because this is the axis along its diameter or diameter of this disk. So moment of inertia for a disk along the diameter is 1 by 4 mr square. So mass of this disk is dm. So I'm writing it 1 by 4 dm r square. But I need the moment of inertia for this small disk component along this axis or about this axis. And for that I am using here the parallel axis theorem, and according to parallel axis theorem I can write di equals to, or I can write it I will be I naught plus m d square. So here the moment of inertia for this small component I can write di, and the moment of inertia about the main axis, which is here, which is 1 by 4 dm r square, and the moment of inertia, the mass of this disk is dm. So I am using dm here, and distance between two axes is x. So here x is. So this is the moment of inertia for this small disk component along this axis. So here it is. So first I just, in this case I know the r, I know the x, but I don't know the dm. So first I write the dm here. So dm I can write the volume of this disk into density of this disc or this cylinder. So dm is small volume of this disc, which is pi r square is its cross section area and thickness is dx. So volume is pi r square dx, and the density mass upon volume of this cylinder, which is pi r square into L. Here I cancel out, so I get dm is m by L into dx. So this is the mass of this small disc component, and I put this mass component here, and I get di is m by L is common and dx is also common, remaining r power 4 by 4 plus x square here and dx here. So this is the moment of inertia for this disc component about this axis, but we have to determine the moment of inertia for complete cylinder, and for that we will integrate this dI and we get the moment of inertia about this axis. So here I put the value integration m by L r power 4 by 4 plus r square by 4 plus x square and dx. So here the limit of this dx or limit of this x, I can take this component here, so x can be L by 2, and if I take this small component here, then x become minus L by 2, so limit will be minus L by 2 to L by 2. And you know this cylinder has a symmetry about this axis, so I can change this limit from 0 to L by 2 and I multiply it with 2. So I am doing that here, 2 integration 0 to L by 2. Okay, I am taking this constant out, m by L, and remaining is inside the integration r square by 4 plus x square, and here dx is. Now we are going to integrate this equation. Before that I need some space, so I am cleaning it up. Please take a screenshot or pause your video and make the notes first, and you can go back also. So here integration, these are the constant 2m by L, and the integration of r square by 4. R square by 4 is constant, and integration of dx is x plus integration of x square with respect to dx is power 1 is increased, power is increased by 1 and increased power comes in the down, and here power 0 to L by 2. So integration I will be 2m by L. When I put the upper limit r square by 4, it will become L by 2 plus here 1 by 3 is constant, and you put L by 2, and this is the Q, and when I put lower limit 0 here and here, it will become 0, so I write 0 here. When I solve it, I can cancel out L here from L here, and this L you can write it, this is the 2Q, so when I cancel it, it will become L square and it will become 2Q. So I solve it, it will become, when I multiply it and I solve it, it will become 1 by 4 m r square, because 2 and 2 will cancel out each other, and here this 1 2 is cancel out, and 2 2 will be remain, so it will become 1 by 12 ml square. So this is the moment of inertia for a solid cylinder.